All right, so hi everyone. I'm Mike Bostock. I work for Square. I've also built a number of open source visualization libraries, Protovis, Polymaps, this thing we released last week called Cube for time series visualization. But tonight I'm really excited to talk about something that's been really like my passion for the last year or so. It's data-driven documents. It's a visualization framework in JavaScript for the web. It's called d3.js for short. But I'm actually not really going to give a good sort of introduction or overview of D3 tonight, because there's sort of a lot to try to fit in 20 minutes, and I thought like if I try to sort of fit everything in, it would feel a little bit fragmented, and I could only give you sort of a superficial, like here's a whole bunch of examples. So what I thought I would do instead was pick one particular application or visualization domain that I found really interesting so that I could do that in more detail. And I think that's actually appropriate because like if we think about tools for visualization, it's great to make that process easier as well, but we should also keep in mind like how those tools shape the types of visualizations that we build, like by making certain things easier or harder. So I'm always really interested in how our visualizations or our tools enable us to make new types of visualizations rather than sort of recreating stuff that we've seen already. So the domain that I'm going to talk about tonight is actually force layouts. And there are a few reasons for that. One is that force layouts are visually interesting. And you can drag them around or whatever and they move. They're sort of fun and engaging. And so like talk should entertain as well as inform. But also the implementations are really interesting. Like there are very sort of simple rules that go into this layout. But yet it has this sort of like beautiful emergent behavior that it's able to produce this layout, which is it's helpful for understanding the structure of this graph just from these simple rules. And they're all like really interesting sort of subtle ways in which the algorithm works that can make some implementations better or worse. Better performance, like whether you use quad trees, for example, or like whether it handles how stable it is when you have particular degenerate graphs. And also I think like force layouts have many interesting applications, even beyond sort of the traditional stuff that we use for understanding graph structure. And I think if you generalize it a little bit, like really what a force layout is doing is providing an implicit way to do a position encoding. And if you've studied like sort of the foundations of InfoVis, you'll know that the position is like the single most important encoding that we have. And so force layouts are nice as a way of sort of moving beyond just sort of a direct mapping, like a linear scale from a data dimension to a position dimension. Instead, like when you have multiple things that you might want to combine together to form your layout. But before I talk about like, this is an example you may have seen before. Before I talk about like how you can sort of extend the force layouts to do more interesting things, like to take advantage of that implicit position encoding, I thought I would talk first a little bit about like how it's used sort of traditionally for understanding graph structure. So this is actually a recreation of this like really horrible infographic that was, horrible in the sense that it was intentionally confusing, like it was just all these like cross lines. And certainly there are a lot of suits going on like in the mobile industry, but the structure of this graph like is actually relatively simple, and you can see there like Apple and Microsoft relatively in the center. And the way that these force layouts are designed is basically to optimize sort of two things. One is that the graph theoretic distance, like the shortest path between two nodes in the graph, should be proportional to the distance of two nodes on the screen, right? So like the shortest path between Microsoft and Apple is 2 hops, so they're closer together than say Apple and Amazon, or the disconnected nodes, which are infinitely far away from a graph theoretic distance. So you've seen these things before. You probably have an intuitive understanding that there's like some physical simulation running behind here that produces this layout. But I wanted to like sort of dive in more detail so that you understand how that works. So I've got like a series of examples that are going to build up to show you sort of how the force layout works under the hood. And then from there we can build up and see how you can then customize it to do sort of more interesting things. And I have like a tiny bit of code here, but these slides are actually already online, so you can see like the full code, and if you have questions, feel free to ask me about it afterwards. So the way these slides work is it's all based on a little particle system. So as I move the mouse around, it's just going to create a dot here. You can see it's just pushing x, y coordinates onto the array of nodes. And then there's a little bit of a transition here so that the dots remove themselves after 3 seconds. Now this is actually a force layout right here, but it's obviously not a very interesting one because there are no links in the graph, there are no forces, the nodes are initialized with no velocity, so they don't move at all. But by just changing one simple thing, which is by initializing the previous position of these nodes to be the previous position of the mouse, then they start moving around, right? So you can see they're sort of sliding here. And this is actually using a system called position relay. It's just a numerical integration system. I mean, there's a lot of different ones that you can use as well that have different characteristics. Position relay is really nice because it's easy to add geometric constraints, and that's actually how the links are implemented. So I'll explain that more in a little bit. But like that sounds like mathy and complicated. But it's actually like these 2 lines of code here, which admittedly are a bit obfuscated, but let me try to explain. So there's one other thing, like in the previous slide, you saw like when I was moving the nodes, they would just sort of slide like they were sliding on ice, like there was no friction. So there's another component here, which is that there's friction. So at every sort of tick of this simulation, the velocity slows down unless there are other forces that are also acting on these nodes. So I shouldn't draw nodes over the code that I'm trying to explain. So what this is actually doing here is relatively simple. So it's recording, remember, the current position of the node and the previous position. So at every tick, all that we're doing is taking the current position and copying it over to the previous position. And then the new current position is just the old position plus the difference between the current position and the previous position, right? So the velocity is the difference between the current position and the previous position. And then we're basically assuming that all of these nodes have constant mass, there's constant friction, right, there's 0.9, and there's a constant time step. So if you make all of these simplifying assumptions, right, we're not building like Quake 2 here, we're just doing force layouts, then you can make it faster and you can also make the implementation pretty simple. But that's not enough by itself. You want to start to have some global structure here. And so the way that that works is each of these particles, rather than being sort of independent, are actually charged particles. There's mutual repulsion. So each charge affects each node affects every other node. And that's basically how the graph doesn't collapse, because, I mean, if you just wanted to draw nodes connected to links, it would be really easy if you didn't care about showing the global structure. But everything would look like just a giant hairball. And so it's the charge force really that's providing the global structure of your layout that helps you achieve that sort of graph theoretic distance optimization. And funny enough, like this is actually one of the few places where performance really matters in terms of doing stuff in the browser. In order to compute these forces, if you did it naively, it would be n squared, where n is the number of nodes that you have. So we actually use this technique that comes from physics, from doing astrophysical simulations of the n-body problem, where you use a quad tree and that allows you to do n log n calculations for these charge forces rather than n squared. And that actually matters if you have something like 500 nodes in your graph that you're trying to lay out. Now, in that case, it was a negative charge force, which meant that all of the nodes were repulsing each other, which is why they were flying off the screen. You can also invert that, in which case they all attract each other, which is sort of a more traditional n-body problem, right, if you wanted to simulate like universes spinning around or whatever. So just by inverting the charge force, you can get this sort of gravitational effect. And you notice like some of the nodes are sort of getting spit out there, which probably wouldn't happen in a real universe. But that's just because of some of like when the nodes get really close together, you essentially get a divide by zero with the inverse square law. So instead what it does is just nudges the nodes a little bit and they get thrown out. So this is not like really an accurate simulation, like if you were doing protein modeling or some like biological simulation where you really depended on accuracy, then this would not be a great choice. But it's a good choice for visualization because it's accurate enough and it's really fast. Now, the reason I brought up attraction here is like if you just have repulsion, then all of your nodes are going to fly off the screen, which obviously isn't a very good visualization because you can't see anything. So you can't just invert the charge force because that would cancel out. So instead what you need is some way to keep the nodes on the screen. So what we do is basically have a gravity force, but it's not gravity, again, like inverse square law. It's really like a virtual spring that connects each of these nodes to the center of the canvas. And the reason for that is that then the force is linearly proportional to distance rather than using an inverse square law, which means that asymptotically the gravity gets stronger and will eventually overpower the charge force as you get farther away from the center. So you see, like, when I add nodes farther away, they move really quickly, but when I add nodes in the middle, they move like relatively slowly. And that's also really good for visualization because it means that you can keep your nodes sort of on the screen in the center of the layout, but you won't get a lot of local distortion. Because really, the goal, again, of these layouts is so that you understand the graph structure, and if you end up distorting the graph structure just to keep the nodes on the screen, then that's a bad thing. So these two forces, if you combine them together, this sort of beautiful thing happens where you get this really stable layout, right? And so this is basically the starting point for how we look at the graph structure. And you can in fact see here as I'm adding a bunch of nodes that it ends up stabilizing on this circular pattern, because that's how at some point the gravity overpowers the charge force, and it happens sort of with this circular symmetry. And this is actually a significant improvement over the Protovis version of the force layouts, which did not have this gravity to keep things in the center. So instead what I was doing with Protovis was actually a bounding box. And what would happen there is if you had a disconnected graph, the disconnected components would just fly towards the edge of the screen, and it was really kind of ugly. But you saw, like in the first example with the patent suits, that these two things work together, not just for the simple graphs where everything is connected, but also for these disconnected graphs like here where everything is perfectly disconnected. So now that we have that sort of as our starting point for doing the global structure, the next thing that we want to look at obviously is links. So in this case what I'm doing is, again, I'm adding a new node every time I move the mouse, but that node is just connected to the previous node. And again, like, they remove themselves after 3 seconds. So this isn't a particularly interesting graph, but it sort of shows the point of how we can understand this graph structure and how those forces work together to produce a nice layout. Now, the way that the links are implemented inside of D3 is actually not using sort of Hooke's law like a traditional spring force. And instead what it does is this thing called constraints relaxation, which sounds, again, fairly complicated, like numerical integration. But it's actually a fairly simple concept. So basically, if you have these two nodes here, A and B, that are connected, right now they're 20 pixels apart, but your link distance is 40 pixels. You want them to be 40 pixels apart. All that you do is you move them 10 pixels apart in opposite directions. And because you're using position relay, all you're tracking is the current position and the previous position. The velocity of these components implicitly gets updated. You're just updating the new position, so you're also changing the velocity at the same time. And unlike if you do Hooke's law for spring forces, typically that approach requires a damping factor, which is dependent on the velocity of the nodes, which of course is not very accurate, where you're only tracking the current position and the previous position. So with the force approach, you end up sort of overshooting your target bounds, whereas with constraints relaxation, you always know exactly where you want to be, and you're just moving towards that point. So it ends up being much more stable, converging on the right layout more quickly, and producing good results. And the other sort of subtle thing that goes into this is that if you want these nodes to be 40 pixels apart, you don't actually move them all the way there. Instead, because typically you have multiple constraints that are acting sort of at the same time on these nodes, there's this alpha parameter, and that's essentially a blending parameter where you're blending multiple constraints. So for example, if that alpha parameter is 0.5, then I'm only going to move them halfway so that they're 30 pixels apart rather than 40 pixels apart. And that helps these sort of conflicting constraints resolve each other more quickly. And now, because this is D3, I haven't really talked about how these things are implemented, but one of the key ideas in D3 is that the layouts are all in data space. They're abstract. They don't dictate a particular visual representation. So it's entirely up to you to determine how you want to display the results of that layout. So in this particular case, rather than drawing circles with lines that are connecting them, I'm just creating sort of a single path element. And I'm using like a thick stroke and like rounded corners and actually like basis interpolation to make this a little bit smoother. So it feels to me like sort of like the square signature screen in a really annoying version. But the point here is just to show you, like, you can change how the force layout is displayed. It's just a data space, and then you can use D3 to determine how that is displayed. Like another example that you could use instead is sort of like these raindrops. So in this case, I'm creating sort of new circles, and rather than those circles being of constant radius, the circles increase from 0 to 80 pixels over the 3 seconds that they live. And they're also changing color, and this is actually using HSL interpolation, which is really nice for data encoding, but it's also really pretty. So it's changing, it's not quite constant hue, it's like 180 degrees to 210 degrees, and it's going from black to white so that it fades out at the same time. So it's really easy to sort of change how you're displaying your data in conjunction with these layouts. And the other thing that I'd like to point out is that it's doing this simulation here of the force layout, but it's also doing the transitions concurrently. So you can see that these dots, or these circles are moving around. The transition is running at the same time. So those two things can work together. So now I'm going to talk about like sort of how you can take this basic idea, right, like of the gravity and of the charge forces, and start to do interesting things that incorporate other aspects of your data. So one thing you can do, rather than using sort of a single gravitational center, is if you had, let's say, categorical data associated with each of your nodes, you could use different foci for each of those categories. And essentially that provides sort of a Gestalt grouping. So here, like, I'm randomly creating nodes of one of 3 categories, and rather than all of them going to the center, they each gravitate towards their own little location. So if you had different categories, you could use them to sort of separate your graph that way. But the nice thing about these forces is they're additive. So if you have multiple forces that you're applying, they end up sort of adding together. So if we had categories that were labels rather than being exclusive, then those end up adding together, right? So you've got sort of these purple nodes, which are actually a combination of the blue and the green, and the pink nodes, which are a combination of blue and orange. And this also applies to the graph structure. So for example, like, okay, let's say again we had categories for our nodes, but rather than just looking at individual disconnected nodes, we started to have like sort of disconnected subgraphs that we wanted to see. So in this case, like when I'm creating the nodes, you can see how they sort of automatically end up aligning in sort of the right place, right? So the nodes that, or the links that are only connected to green are down here in the corner, whereas the ones that are connected to both green and to blue end up being in the middle, and they end up being sort of like, you know, magnetic filaments. They end up being sort of aligned along those 2 axes. So this is a really powerful way to sort of take, especially when you have like mostly disconnected graph, to try to orient them into a particular location and try to show other aspects of your data rather than just strictly the graph structure. And to give you sort of like a more concrete example, this is a recreation of something I saw in the New York Times, so just showing the 2008 Olympic medals. So again, gold, silver, and bronze. And so in this case, like each of these nodes here gravitate towards the centroid of the associated country, right, the United States, or Russia, or China. This is maybe not like the best visualization, particularly like in these areas right here. It's a little bit hard when you have countries that are close together to differentiate those two. So a better approach actually for this sort of thing, and more close to what the New York Times used, is called a Dorling cartogram. And this is not quite a Dorling cartogram because all of the country, or all of the states here are exactly the same size as they are normally. They're just showing a value of 1 essentially. But the idea behind a Dorling cartogram is that you take all of the different geographic areas and you distort them to the data that you want to show, for example, like the number of Olympic medals. But then you take your geographic areas and you actually connect them so that they're part of a mesh, so that any area shares a link with another area that they share a border with. So for example, like California and Nevada here share a link, or Oregon. But this is actually, I didn't have data that showed sort of where the shared boundaries were for this particular GeoJSON file. So what I did is sort of like really geeky, but I took the Delaunay triangulation of the centroids of these areas and then created a mesh from that. So like each of these points here is just computed, it's the centroid of these polygons. And then the Delaunay triangulation is a simple way of making a triangular mesh from that. But it's not like a perfectly accurate solution, right? Like you can see here, Maine is connected to all these other states that it doesn't share a border with. which can cause like some sort of weird behavior, and it's not as stable as it should be. But hopefully that shows you the point of like how you can build these things and start to do interesting things.
Wow.
Now you can have quantitative foci as well, right? If you have quantitative data that you want to show. We're doing some interesting stuff internal to Square, which unfortunately I can't show you right now, but this still shows you like we're taking essentially one position dimension here, the y position, and using that to encode some quantitative data. Like if you were looking at like web traffic latency, for example, and you wanted to look at like maybe a sequence of events, you could use the y-axis to show the latency of those requests, as well as combining that with some other sort of topology or relationship that you want to show. So it doesn't have to be strictly categorical for that technique. Now, another sort of area where you can do interesting things with forest layouts is looking at tree structures or trees. There are special layouts for trees as well. Excuse me. There are tree layouts, tree maps and partition layouts, cluster layouts, that sort of thing. But forest layouts are also really quite good for looking at trees, again, especially if you have other data that you want to show as well. And we can use some of the techniques that I talked about to try to reveal that tree structure more directly. So in the previous slide, it wasn't necessarily that obvious, like which node was the root node, whereas in this slide, it's perfectly obvious because that node is up here at the top. And the way that this slide works is that each of these nodes here, each of the children, rather than, again, gravitating towards the center, gravitates towards a position beneath its parent node, right? So this node that I'm grabbing is actually gravitating towards like this location right here under the parent, and so on for all of these other nodes underneath. And the nice thing about this approach is that it's really good for sort of preserving the local tree, right? So I can drag this thing around, and it tends to be relatively stable. And I can grab sort of this subgraph here, or subtree, and move it around, and it's stable like within its own space as well. But you can see that it's not really like a perfect sort of deterministic tree layout. Like in particular, like this case right here on the left side, these nodes are getting stretched out because there are many more child nodes here that end up pulling it because of this repulsion between all of the charged nodes. Now, if you wanted to do sort of have a little bit more accuracy, but make some other trade-offs, a different approach is more like the quantitative foci slide. And in that case, what you're doing is computing the depth for each of your nodes based on the distance from the root, and then having them gravitate along the y-axis towards that particular depth. So in this case, like if I grab the root node, I can't drag the whole thing around. It no longer preserves that sort of subtree structure, but perhaps the results are better overall because you have sort of better depth banding for your tree. So that's two different ways that you can start to show like tree structure for your data. Another technique that you can look at is collision detection. So if you have, you can use charge forces to prevent nodes from collapsing on each other, but you can also use collision detection, which basically looks to see if two nodes are overlapping in space. So in this case, what I've done is initialize sort of a whole bunch of nodes with a random radius, and then have one invisible node at the mouse location, which causes these other nodes to be pushed away from it. And the way that you know that this is using collision detection rather than just sort of charge forces that are repelling each other is that because these circles have different radiuses or radii, the smaller ones actually tend to sort of squeeze between the larger ones and get caught in the middle, a bit like if you have sand caught within rocks. And so you can see as I move these circles around that the smaller nodes end up getting caught in the middle. I have a few other examples as well. I'm not sure sort of how much time I have left. But just to give you sort of like the full gamut, I guess, of different things you can do. So I mentioned using a bounding box. So in this particular case, what I've done is turn off the gravity and instead use that bounding box approach, which maybe is nice if you have sort of a fixed area that you want to show your graph in, but is a little bit harder to deal with because your graph doesn't quite end up center in the layout. And of course, if you do end up actually using the bounding box, then it's just distorting your graph and making it hard to look at anyway. And again, so D3 has sort of total flexibility in how you do this, how you control the visual representation. So in this case, rather than just doing sort of circles and lines, what I've done is take a little smiley face image, and then I've added a bunch of labels so that you can sort of see what these nodes mean, rather than sort of waiting until mouse over and showing a tooltip. And this is a graph looking at co-occurrence of characters in Les Miserables. Another example, just quickly. So again, this is a tree diagram, the same tree as before. But what I've done is size the nodes according to a quantitative dimension of data. Like this is actually the Flare package hierarchy. It's sort of my common example for all this hierarchical data because it's really easy and it's pretty. But in this case, like each of these circles here corresponds to a class, and the size of the circle is the number of bytes in the source file. But this tree is collapsible, so I can take these nodes and sort of collapse them into single points, or I can click on them and sort of expand them again. So I think probably like this could be a little bit better if the node sort of got sucked in rather than sort of collapsing immediately, and sort of having these package nodes that get collapsed have like more repulsion, so they stick farther out. But anyway, I just cooked it up quickly just to show you sort of different interaction techniques. And then lastly, like this is something I really enjoyed that I created sort of to help debug the force layout as I was implementing it. It's online and you can play with it as well. So if you want to sort of understand in more detail how the force layout works, basically what it does is every time you click, it's going to add a new node. And any other node that's within this red circle here is going to be connected. So it makes it really easy to sort of click a few times and build up some graph structure, and then you can drag it around and play with it. And you can also just sort of click a whole bunch of times to add random stuff, or like make these, if I can get this like little components. Anyway, it's a lot of fun. So that's all I have to say. But check these examples out online, and I'll post a link to the code and stuff. So thank you.